Okay, this is Ryan Noble, and I'm going to be explaining Table 1 of the article. The authors Gonzalo de Gonzalo, Christian Smith, Jianfeng Jin, Adrian Menard, and Marco W. Freihe are addressing the question of turning a riboflavin-binding protein into a self-sufficient monooxygenase by cofactor design. The question of turning a riboflavin-binding protein into a self-sufficient monooxygenases are prepared by cofactor design. Tight binding of nitrogen acylated flavins to riboflavin-binding proteins resulted in the creation of artificial flavoenzymes capable of hydrogen peroxide-driven and antioselective sulfoxidations. Opposite and antioselectivities were achieved by altering the flavin structure in accordance with the binding mode predicted by in silico flavin protein docking of the unnatural flavin cofactors. The purpose of the study was to show that cofactor redesign is a viable approach to create artificial flavoenzymes with unprecedented activities. Monooxygenases perform selective oxidations of organic substrates under environmentally benign conditions. Due to this and their chemoregio and antioselectivity, monooxygenases are regarded as extremely valuable biocatalysts. Nonetheless, this application of monooxygenases is often determined by their dependence on nicotinamide cofactors, NAD, P, and H. These cofactors are required to deliver electrons to the oxidizing cofactor, such as P450 monooxygenases and flavin and flavoprotein monooxygenases, enabling the enzymes to utilize dioxygen for oxygenations. Several strategies to circumvent the stoichiometric use of nicotinamide cofactors have been reported. Two of these approaches, the use of additional biocatalysts in combination with a sacrificial co-substrate, has been the most effective. And nevertheless, the use of cofactor-independent monooxygenases is far less complicated and has been demonstrated for a few monooxygenases. This table 1 shows the antioselective peroxide-driven sulfoxidation of prochiral sulfide by riboflavin binding protein complexed with modified flavins. As you can see, there is a 5.0 mm substrate, 50 micrometers of riboflavin binding proteins catalyst, and a reaction time of 24 hours. The convergence we see here was determined by gas chromatography. Gas chromatography separates chemicals based on their volatility or ease with which they evaporate into a gas. The chemicals in the mixture separate based on their volatility, and small molecules travel more quickly than larger molecules. So it basically just separates the components of a mixture. In the table, the authors reconstituted apo-riboflavin binding proteins with different flavins, shown here, 2, 3, 4, 5, 6, and the controls. They then derived synthetic flavoproteins that were tested for their ability to perform peroxide-driven and antioselective sulfoxidations. They observed that the created artificial flavoproteins were active as catalysts and even displayed enantioselectivity. Here we can see for entries 1 to 4 that use the methylated monooxygenase show a convergence between 37 to 55%, while their EE is between 30 to 10%, which was measured through gas chromatography or HPLC as well. We can see that using a flavin of 3, there is a 40 to 45% convergence and a slightly less amount of EE. For a flavin 4, you can see the monooxygenases show a consistently high percentage of convergence, shown here from 48 to 40, and about the same amount of EE percentage. For a flavin of 5, they also show quite a high percentage of convergence. For 6, they show the highest amount of convergence. However, they also show the lowest amount, they also show the highest amount of EE. And for the controls, we see the ones without this protein do not show too high of a convergence percentage, and all 3 of the last ones that are controls show an EE of less than 3%, which shows the way that the cofactor redesign is a viable approach to create artificial flavoenzymes with unprecedented activities. And that's about it for the table.